So start with this valve. Explanations are the fuel of progress. The fundamental tool through which humans gain control over the future, like with the COVID vaccine. But so far, only human scientists could craft this extraordinary symbolic series. However, recent AI breakthroughs suggest that the possibility of machines aiding us in this task. Actually, not mere tool empowering scientists, but rather peers capable of producing original research and pushing forward knowledge out of this world. So this was my vision at the beginning of this PhD, coming also maybe from my bachelor in physics. And actually I managed to have a lot of fun in my PhD. I'm Antonio Norelli, and today I will talk to you about artificial scientific discovery. I'm an early PhD candidate in computer science in Sapienza, in the Gladio Research Group, advised by Professor Emanuele Redola. My earliest exchange advisor was Prof. Francesco Papetello. I spent with him 6 months in AWS Tübingen, while the reviewers of my thesis were Andrew Lampinen, Senior Research Scientist at DeepMind, and Professor Alex Brostin from Technion, where I spent also 4 months in his Vista lab. But let's start with an overview of my PhD. Year by year, so this was 2020. We got published oral and link, actually oral at ECCV. And also I was a TESI co-advisor on a couple of theses and be a teaching assistant for the deep learning and applied AI course here in Sapienza. Next year was this big work on explanatory learning that finally we presented this year at a workshop at SML. Then we have other works, including this big bench published on transactional machine learning research. And also I was the representative of PhD students and organized the workshop for all PhD students, 4 days, talks. It was very nice in Bertinoro. 2023 was the best year relative to scientific products. We have another tech year, 2 paper ads, NEWIPs, also a workshop, so it was quite fun. So yeah, that's the review of the products of my PhD. But today I will talk you about 4 of them. The one I was the project leader, and that also made my thesis about artificial scientific discovery. Specifically, we will not see all the works in detail, but rather we will take a single thing from each work. And we will start with Oliver, responsible of a crucial realization. So, maybe most of you remember this moment. This is all World Go champion losing against the machine. And this was really a cornerstone in the progress of AI. Actually, the next model, AlphaGo Zero, to me was even more impressive, and actually a very promising starting point for artificial scientists, because AlphaGo Zero was able to, starting only from the rules of Go, to discover all Go knowledge from scratch and defeating the best human player. So I went deep on this work. Okay, can AlphaGo Zero be a model for artificial scientists? Demonstrated to discover all this Go knowledge. And how we did it, actually, we replicated the result on AlphaGo Zero on another game, Otello. We even defeated the Italian Otello champion. This is our work with Professor Panconesi, and we even challenged a former world champion But all of this work to arrive to a fundamental realization. AlphaGo Zero and our program Oliver are missing a fundamental trait of a scientist. That is being able to communicate their discoveries. AlphaGo Zero, Oliver are not able to write a book about Go, about what they have discovered to make other people improve. So this means that we have to take a step back and ponder about what is the fundamental problem solved by scientists and trying to model this problem. So, yes, making discoveries, but also communicating these discoveries. And we took inspiration from another board game, Zendo. In this board game, one player plays the nature, the other players are the scientists. The nature knows a secret rule. For example, in this case, at least one blue. This is secret. And then the scientists, at their turn, make experiments. And the nature tell if this structure made by the scientist is coherent with the secret rule or not. In this case, it's coherent. There is at least one blue. The scientists take turn making experiments, the nature tag them, until a scientist have an hypothesis. Oh, I think that the law of nature of this phenomenon is one or more blue. Okay, so what happens in this game? Happens that you call another scientist, and you give it to him the hypothesis. He has no experience of this phenomenon, and now he should be able to tag properly many structures from this phenomenon. And the nature, the player playing the nature, oversee this. If he managed to tag properly all these structures, then the player who proposes the conjecture is said to be the winner. So this is the idea. Okay, so what we want to do, we want to put a machine in place of a scientist and solve the problem. So to try to get how we can do this, let's try to be a machine. So try to solve the next game. Let's suppose we already have some experiments. You have some conjectures or some comments about this problem?
I've read the paper.
Okay, maybe there is silence because it seems that something is missing in this problem. Like, what is the format of the rules? Which attributes may appear in the rules? Posso dire la regola in italiano? Maybe someone already got the rule in another language. So yeah, there is another fundamental problem. So this problem is still not well defined because we should, in a way, define the language in which we want these explanations. So the language should be given, but how? Now, a possibility is to hard-code a rigid language interpreter in our artificial scientists, like we hard-code a Python interpreter. Now, this is a problem, this is a fundamental limitation, because the frontiers of knowledge are also the frontiers of language. Let me make you an example. Take the seminal paper of Claude Shannon about information theory. In this paper, Shannon introduced for the first time the concept of entropy in information theory. And actually, this idea of entropy in this paper is, on some sense, similar, but also quite different from the common idea of entropy. So if you have a rigid interpreter of the word entropy, you're not able to appreciate and make a step forward in your knowledge. So we cannot hard-code the interpreter. We need an interpreter capable of original interpretations, like the thing that Shannon did. And that means to us, our realization was that this means that the interpreter should be learned. So our problem of the scientists now have a third point. Our machine should also learn how to interpret symbols. Okay. So the machine should learn, but from what? What do we have to learn? From past explained phenomena. So this is a new phenomenon, unknown, we don't know the explanation, but reasonably we assume to have some phenomena already explained. So for that we have many observations and the explanation. The language is unknown. We have to learn this language from here. This is kind of a science book. This is kind of the situation of a baby that want to become a scientist. So first have to understand the language. So our machine should learn the language over this explained phenomena. And this also kind of model, called the idea of climbing the shoulder of the giants. So that's our formalization of the problem of the scientist. We call it the explanatory learning problem. Actually, we also propose a solution to this problem, but I will point you to the paper if you want to know more about this. Today I just wanted to let you understand the problem. Actually, this paper was quite well received. We have comments from Julia Pearl. I also was invited at the Simons Institute in Berkeley to give a talk about it. So yeah, this is our second step. A true artificial scientist can only emerge when a machine can autonomously interpret symbols. Okay. Now let's go to the third step. So with explanatory learning, we learn how crucial is the problem of interpreting language in science for a scientist, and specifically how is the link between symbols and their meanings. So we went deeper and asked to ourselves, how is this link between signs and meanings created? So to make a concrete example, how can I build a model that is able to couple correctly images with their captions and build this link? So actually, this problem was quite successfully solved in these deep learning years, specifically by CLIP, this model that was a revolution in computer vision, that took two big neural encoders trained from scratch on a huge amount of image text pairs. 1 year later, Google showed that you can build the same model, but you can train only the text encoder. So, you take a frozen pre-trained image encoder, you can train just the text encoder to match the representation of the images. This solution definitely works, but they are quite expensive. You have to train on hundreds of millions of pairs, and also it's not completely satisfying. Like, yeah, they build this link, but it is inside this black box. You cannot really understand what is happening. So, can we do something in the open light of the sun? And that's what we did with ASIF, where we managed to build a clip-like model, but using only two frozen pre-trained encoders. One that only has seen images, so that have no information about things in images or name, and an encoder for text that have never seen a dog or any image. We are able to pair these two frozen pre-trained models to build a clip-like model without any further training, but using only a small amount of image text pairs. Now, the idea is very simple, but I will pass over for the time. Maybe I can take a question on this. But this is our tentative answer to the question of how is the link between scenes and meanings created. Yeah, you can read more in our paper. presented at NEWRIPS this year. Okay, so finally we arrive to Big Bench, where I want to show you a result, and I want to answer to a question that maybe some of you is asking in their minds, like, now is 1 year or some months that ChatGPT is in the world, and is kind of realizing the vision of this famous movie, Her, of Samantha, of an assistant being able to help us in our work. Maybe ChatGPT and large language models are already a first version of artificial scientists. Like, I do not have a definitive answer, but I want to show you a result of our lab. This was actually a spin-off of the explanatory learning work I told you before. And we participated to this collaborative effort to test large language models called Big Bench. So people scientists from many universities could contribute with a task to test large language models to see how good they are. In the end, were collected more than 200 tasks by 450 authors across 132 institutions. This work was published in 2023 and it was quite influential already. It has more than 500 citations because people are using it to test new models, to compare models. And we proposed that a collection of tasks in Big Bench, actually a task derived from the problem I explained you before, from explanatory learning. This is an example of the kind of question we pose to the language models. So we have two structures like the one you saw before, and we ask the language model which is the rule that is consistent with the first and not consistent with the second. And actually we have different versions of this task where we try to make things harder to investigate how the interpretation of symbol is working inside the language model. So we define sometimes adversarially the link between the scene and the meaning. So for example, we say that this is a red square. Okay, so our task was selected for the 24 tasks that made Big Bench live. Like the benchmark was very big, so they selected only 24 tasks for quick tests, including ours. And actually, our task across all the Big Bench-like tasks was the one showing the largest gap between human and machine performance. Like, here you see the performance of human. Here is the average performance over many tests. Here is the best performance. You see our task is perfectly solved by the best humans, and also it's hard, but solved by many other humans. While the best language models only do random chance, because we have 5 possible answers and we are not significantly away from 20%. And this is the largest gap across the Big Bench live benchmark. Okay, so this was the last thing I wanted to show you. So we have first this realization. We're missing something from the problem of the scientist from alpha to 0. Then we defined back this problem of the artificial scientist. We realized how much interpreting language is crucial and is the big part of the problem, and we proposed an idea to solve it, and then we saw that maybe ChatGPT still needs something else. So, thank you, and I'm ready to take questions.